talk when your session is up. And when we are in the question and answers periods after the talks, I would ask you to just answer your questions in the chat window you have on the left, lower left side. And the speaker will repeat your question and then answer it. That works best with so many attendees. Okay, so with that said, I will switch the presentation to the first presenter, Comau. And I will give the word to Elisa and Fabrizio.
Yeah.
Hi. Hi, hello.
Hello to everybody. Can you hear me?
Yes, we can hear you.
Yeah.
Okay, great. So can I start?
Yes, you can start. You should see your slides and you can start.
Yes, great. Okay. Hello to everybody. I'm Fabrizio Romanelli from Comau Robotics, and going to present you something about the Comau controller's evolution from C4G and to C5G Open, and to slightly show you also something about ROS. Here, as a summary, we want just to give you an introduction on what is a robot open controller, and then we want to show you our past C4G open control and ORL library. Then we just go ahead to the evolution of our open controller, starting from the requirements and improvements from the, let's say, past open platform to go into the C5G open and then to the ROS integration of our open controller. So the open concept is something that we can try to summarize as an approach to add the standard robot control unit the possibility to improve its power, giving from example for an external personal computer. This can help both programming the automation of robotic cells and also to give an integration with external sensor, as we can see from the picture. So we can think of implementing vision algorithms to look and move, or visual serving, or whatever, interaction algorithms like force control or impedance control, or also something like CAD planning for surface movements and complex interferences. Anyway, the open architecture, as we conceived it in Comau, allows to develop new innovative motion strategies. Here we have a past very strong in the open control, as you can see from this picture. As we have a lot of systems in Italy, we have also a lot of systems in Europe, and something out there in both the world, with also some kind of let's say dissemination on with the University of Napoli and through other European projects where we used and showed the potentialities of the C4G Open. We also start to plan an open community on the web in order to put together both students, researchers, integrators, and companies together with the Comau experienced staff and engineers to share all the ideas and all the possibilities of the C4G Open all together. So what is a C4G Open? The C4G Open is basically platform, both software and hardware, that could be used to, let's say, developed new techniques for robot controller and trajectory generation that can be added to the standard robot Comau robot control. So this can add the possibility to complex and sophisticated real-time applications that can involve multiple technologies. So we can think about passing from a standard platform, as on the left side of the picture, where the standard C4G platform can be used to be connected with the user through several interfaces, to a new open concept where the user can also go to a very low level of controlling the system, the robot system. An important feature of this control kind of open control is that the C4G Open can dynamically switch between the classic, let's say, behavior of the controller, the robot controller, and the open mode. So without any needs of turning off the motors or driving off or whatever, but just programming the robots in these two ways. Let's say the classical way and the open mode. At the end of the C4G Open project, we also added a library to support the other possibilities to control at a higher level the robots, and we developed within the RoboFoot European project the ORL, that's to say Open Realistic Robot Library, that could be used both for the computational direct and inverse kinematics of the robots, for all the robot families for the Comau robots. It can also add the possibility to manage the errors of position or joint ranges, and also to integrate the trajectory generator and interpolator by Comau. But now we also achieved these results, and we want to go further on, and we want to take again the open concept of our controller, open controller, as we can see, so to expand the possibilities of the standard platform. But now we are talking about the standard C5G controller, so our new controller. And we want to improve what we, let's say, what we add with the C5G, with the C4G open controller. So the hardware is dedicated in our new platform and is provided by B&R, a company that is also providing some parts of our new C4G controller. We have the software is based on the Ubuntu distribution, and it is patched to provide a fast communication rate at 400 microseconds. We have developed also the ERL, it means the enhanced Open Realistic Robot Library, to reason both in Cartesian world and joint world, but also to manage multi-arm configuration, and also to manage the communication, but we can see it further on. We also provided the user with a graphical viewer. This means that the user have the possibility to visualize the 3D model of the robot while it is moving on its PC, and we also have started this important part in our project, that is the ROS Industrial interface. That it means that we want to provide an open system that is ready to host the ROS Industrial model that is in development together with people from Padua. We also have the simulator feature that can let the system be used also in simulation mode, and this is very useful because while we are testing our application developed basically in an open way in our open PC, we want to provide a simulation environment where we can test all our algorithms before going to the real robot. So it is quite easy to install and to maintain. Here the open functionality is basically flexible as the C4G Open. This means that we can pass between modes, normal modes or open modes, in a very, very easy and instant way. So the switches between let's say the blue modes that are the normal mode and the green modes that are the open modes are instantly achievable. And this gives a very interesting and flexible way of programming the robots. Here we want to show just a little bit the architecture of the C5G Open, where we have in the right black box the standard architecture of the robot, that is the APC, and on the left side we have the LPC, that stands for Linux PC, that is very powerful, and it allows the user to be directly connected to the standard C5G robot control with real-time communication. So for what concerns the software part, we have the enhanced open realistic robot library that is divided into the ERL motion for computing direct inverse kinematics, Comau trajectory generator and interpolator, dynamic model and Jacobian, and the open communication. That this part of the library includes all the communication management, and it can be used to read real robot data and to send targets and deltas to the real robot at a very high rate of 400 microseconds in hard real time. It is important also to notice, as we said before, the simulation feature. So it is available for all the open modalities to connect to the robots, and this allows the user to work also in a completely safe condition without moving the real robot, but just moving the model on our simulator. So for what concerns the software architecture, to go just a little bit in deeper detail, we have on the left side our C5G standard controller, where we have all the levels for the user application with our programming language PDL2 and with all the levels. And this standard control is connected through two levels, that is the TCP/IP connection, that is the basic standard connection for all the user to be used with the Open LPC, and the Ethernet power link at the real-time connection to be used with the ERL module. So as we saw on the right side of the picture, we have the Open LPC software architecture, where the user can both program its own application at a very low level with the C language, but it also can use the tools from the ERL library for the open communication on the real-time side, and the ERL motion to control the direct inverse kinematics and all the motion stuff for what concerns the robots. And we have also other tools. On these two parts of the libraries, we also have depicted the ROS Industrial interface, that is what the module, the Comau module, ROS module, could be in the future, integrating both the communication and the motion side of this system. So at last, we can say that the user in our C5G Open Next architecture could be capable of both programming at a very high level with the PDL2 programming language. It can also program at a high level with the URL programming through the open mode, and it can also program, do ROS compliant programming, and this is quite important because our architecture aims to put ROS Industrial in a very tight connection with our system. So I left the word to Elisa.
Thanks, Fabrizio. Hello, everyone. I'm Elisa from University of Padua. Do you hear me?
Yes.
Okay. We'll talk about how we technically interface the Comau robot controller to ROS. As Fabrizio said, the Comau controller is real-time, and as most of you know, ROS is still not real-time. So we developed a non-real-time ROS interface for a real-time controller. This is the same slide you saw before, so this is the initial Comau system. We extended this system in order to be ROS compliant. And first of all, we wrapped the existing modules in ROS, and so in this way, existing features persist, but now you can also control the robot using ROS. And moreover, now you can control the robot using ORL library, but you can also control the robot using other ROS compliant library, like for example MoveIt. In detail, the user sends a ROS message to the system. ROS redirects the message with a request to the motion library, and so ORL, MoveIt, and so on. And then the motion library answers sending the ROS message with the motion primitive that the controller needs to move the robot. Moreover, we wanted to give the possibility also to non-ROS compliant system to use this interface. And this is why we developed a TCP/IP connection, which lets a no-user framework to be interfaces to this system with a very common and flexible connection. Finally, now you can control both a real robot and a virtual robot inside the simulator. Precisely, we developed a plugin to control the robot inside Gazebo, but as you probably know, you can use the virtual model of the robot within any ROS compliant simulator, and so Gazebo, but also, for example, VREP. And an important thing I want to highlight is that the open technology lets the user to bypass ORL and C4G and let the user to develop his own controller, and so to control the robot using this controller. And another thing I want to highlight is that the system we developed use the same controller to move both the robot inside the simulator and the real robot. And most of existing systems use the producer controller for the real robot and different controllers for the virtual environment, because the robot manufacturer doesn't not provide it. Instead, our collaboration with Fabrizio and with Comau allows us to use the same controller for both platforms. And in these ways, trajectories are interpolated in the same way. So we use the same controller both for the real environment and for the simulated one. If I want to concentrate my attention in what is the simulated part, I can say that we developed two packages. One which created a virtual model of the robot, and another package which creates a plugin integrating the controller in Gazebo. The first, as I said, controls or creates the model of the robot, and so it contains the robot meshes, and you have the file, and so the robot structure, the dynamic parameters, the kinematic characteristics, and so on. The other one instead creates the plugin of the robot, and so we connect the robot controller to the simulator. And to ensure the same trajectory interpolation of the real robot, we developed a wrapper for ORL, and in this way the simulated robot performs the same movement as the real one. Instead, if we focus on it, I can say that we face two types of problems. On one hand, we have the robot communication that is hard real time. In fact, its frame rate is 2 milliseconds, and on the other hand, ROS is not real time. We faced these problems creating a communication node which includes a real-time thread and a normal priority thread. The real-time thread contains the real robot connection, and the normal priority thread contains the motion data, and so ROS messages, TCP/IP connections, and so on. And I want to highlight that this type of structures let us external controllers to provide real robot movements. In these slides, there was a video, but the PDF conversion does not permit to see it. But I want to link the YouTube video, and I post it in the chat. So if you want to see the movement of the real robot and the simulated robot, you can find it in the link I just posted in the chat. I can say that if I move the slider, both the real robot and the simulated one moves in the same way, because as I said before, we use the same controller, and so trajectories are interpolated in the same way. But I can give another example. We used this system to create two tasks. We use learning from demonstration to create these tasks. The first, you can see in the right, is a velocity control, and the other is a position control. In the position control, we move the box along a linear path, and the robot moves in the same way both in simulation and in the real world, and the other is the velocity controller. And in this task, the robot has to stop an object in motion in front of it. And this is all. I want to thank you. And if you have any questions, you are welcome.
So thank you for the very interesting talk. So as I said before, the best way of the question answer session would be if you just post your questions in the chat window, as you do already. And yeah, maybe Fabrizio and Elisa just repeat the question and then try to answer it, maybe.
Yeah.
Okay.
I was someone from Nicholas Lozier just asked me for the cost of the LPC. Said it's almost near 1,800 dollars, but this is just the cost of the, of the LPC. It's quite different for what concerns all the C5G open. Both the solution with the hardware and the software. But now I can't quantify the exact price, but we can just keep in touch to make you know if it's the question. I saw also Michael Lambert from Montreal asking me if the LPC requires a C5G robot controller. It is actually the answer is yes. It needs a C5G controller because with the C4G open controller, there the problem was that the communication was made based on the RTNet. So this means that the base connection of the C4G open with the external PC in the past were made with the RTNet, but now we have switched to a more, let's say, to a more stable version of communication, real-time communication, that is the Open Power Link communication. Open Power Link, you can find whatever you need, also the source code on the internet, on SourceForge, and we just choose to use this solution of Open Power Link because inside our system, inside our C5G standard controller, we use the Open Power Link as a communication inside the controller. So the standard of our communication protocol is PowerLink, and we thought that a good approach to make the open control more industry, let's say, on the industry side, could be to use an open version of the PowerLink. So another. You still need an RTNet link between the PC and the robot. So this question for the it was true for the C4G as said, but it's not true in the C5G because we need this Open Power Link connection. And from Sean Edwards, is the code available open source somewhere? For what concerns the communication, yes. It's the Open Power Link is open source actually, and for what concerns our ERL library, it's we give it as license, and we ask the user to use directly the functions, for example, to compute direct or inverse kinematics. From let's say a document, a specification document where we have documented all the functions that the user can use to call the open communication modalities or the motion parameters for the robot. Yes, of course. Okay, here is the link for the Open Power Link. Another question, looks like the ROS interface is compatible with the C4G. Is it the case? Yes, it's actually the case. We started to develop together with University of Padua the first modules on the C4G, because while we were developing this part of ROS interface, we were also developing the new C5G Open, so we didn't have all the architecture ready or done to make all the integration of the ROS interface, but actually the approach was almost the same that we used to integrate in our past work the ROS interface for the C5G Open. Sorry, but if Stefano or Elisa wants to add something about this topic.
Okay. I think there are no more questions, right? Okay, so then thank you for your very interesting talk. We will conclude this part of the forum now. Yeah, thank you a lot for this. Also for answering the questions. And there was a question already in the chat. The whole forum is recorded also on video, so we can share the link later on, and so you can rewatch it if you want, and also look for the slides again. Now the next point on the agenda are the lightning talks, and we will start with the first lightning talk from SwRI. From Chris Lewis on the industrial calibration package. So, Luis, are you there?
Yes, I'm here. Can you hear me?
Yes, we can hear you good.
Okay,
so
great.
Go ahead.
Yes, I'm working to develop an industrial calibration package, and the goal of this is to facilitate the creation and execution of high-quality calibration procedures for photogrammetry and robotic systems. So the idea is that whenever the system on a factory floor discovers that it needs to be recalibrated or something gets moved, then the workers on the floor would be able to use the script that's been defined by the engineer to recalibrate. And so that the engineer will use this by defining a set of data capture scenes that includes definitions of all the cameras and the targets and how those when the scenes get set up, whether a trigger to indicate that the scene is ready for data collection and to trigger the cameras and those kinds of things. And currently those scenes and the camera definitions and targets are all defined in YAML files, but we intend to create a GUI to aid in this creation process. And the software will process these scenes to collect the data and then present the problem the bundle adjustment problem to the Google's SwRI optimization package for solving. And we intend to have this package work for both intrinsic calibration and extrinsic calibration of multiple cameras, of calibrating the camera to the robot, all those kinds of things. And some of the key features of this package currently are that we have a custom reprojection error functions that that work for the typical targets for a grid of circles or a checkerboard, those kinds of things. And for example, we parameterize the reprojection error of a target with 6 degrees of freedom for the target's pose and 3 degrees of freedom for each of the fiducials. So a 10 by 10 circle grid would have, it has 100 fiducials, but then it has 306 parameters. And what this allows us to do is to actually calibrate the target itself and determine things like the printing errors and the out-of-planar nature of the target, so that we'll get better intrinsic calibration of the camera ultimately. We also do some interesting things to compensate for the shift in the observed center of a circle when it's viewed from oblique angles. So that's one of the, I'll call it the research contribution that we've made. Okay, we have a variety of interfaces to ROS, including different kinds of camera observers, and these are basically just objects that collect data from the camera, where you define the target and it makes the observations. We have ROS transform interfaces, which allows you to use the TF mechanism for asking where is the robot that might be holding the target. You can ask it to give you those transforms so that when you do trigger it, it knows where the target was for that observation. And then we have triggers for scenes and for cameras. That it can be just as simple as setting the ROS parameter, or an action trigger where the robot needs to move from one location to another to take for the next scene. And so you need to know when that action has been completed in order to collect the next set of data. And so those are sort of aspects that we have implemented. Okay, so on the we have the software on GitHub, which we have a link to here, and then we also have a tutorial, and this tutorial applies to a slightly older version of the code. It's fairly simple. It just did a single
Hello, Chris. I guess the connection is gone. Clay, are you still there?
I don't think they can see that. Let me
Hello?
type it into the.
Hello, are you? We're still here.
Okay, great. Chris was gone, I guess.
No, I'm still here. I was.
Oh, okay,
continuing.
sorry. Okay, yeah, you can continue. Yes.
Okay, so we were going to try to display the video, but
I just put it out here.
we've created a link to the video on the chat site if you'd like to look at the video.
You want to try and talk about the video?
Yeah, let's just move on to the next slide.
Okay.
Okay, and so one of the needs that we have for this calibration tool is we'd like to be able to calibrate the offset between a camera and the tool point when you mount the camera on the wrist. And so the main issue there is that we're not exactly certain how many different poses of if you're going to view a target from that camera, how many different poses do you need to fully constrain that transform, that unknown transform. And again, there's an unknown transform from the robot base to the target, but also an unknown transform from the tool endpoint to wherever you mounted the camera. And so we know we can't do that with just one pose and one image, but we're not sure exactly how many one would need. And so we'd like to basically express this as a need, and then find if you can then determine how many observations you need, then what is the best way to create those scenes. Okay, so I think that's all I have. So.
Okay, thanks a lot. If you have questions, please save them for the end of the lightning talk question, or put them already in the chat window, and we will try to record them. The next talk will be on the ROS control framework. So Adolfo from PAL Robotics prepared a slide set, and I will just change it. So Adolfo, you should see your slides and go ahead.
Hello everybody, I assume that you can hear me.
Yes, we can hear you.
Okay, so I'm going to get started. Yeah, so this talk is about, it will give a brief overview of the ROS control project and what this could mean for the ROS Industrial initiative. So I would like to get started giving an overview of the goals for the project. So we found out that more often than not, the entry barrier for exposing new hardware to ROS is rather high, and this can be a rather frustrating experience. So one of the main goals of ROS control is to lower this barrier, and also to promote the reuse of control code in the same way that ROS has enabled the sharing of higher level code. Another important goal is to provide ready-to-use tools, a set of tools such as controllers that expose standard ROS interfaces, a controller manager for handling the life cycle of a controller, such as loading it, starting it, stopping it, and unloading it. There is also a simulation backend for the gazebo simulator, and then a bunch of building blocks such as a PAD loop, mechanical transmissions, joint limits, and so on. Another important aspect is that ROS control is real-time ready, in the sense that if your application has either soft or hard real-time requirements, then you can use ROS control. But if, on the other hand, you have an application that doesn't really require any real-time, doesn't have real-time constraints, then it's not imposed on you. So now that we move on, I would like to present you this diagram that tries to convey the big picture of a system in which ROS control is present. So at the right, you have your robot. A typical robot scenario involves having an actual hardware platform, but you also have usually a simulation of your robot. And then here, where you can see robot hardware, this would represent the actual software representation of your robot. So every robot has a set of resources that it exposes. These resources can be joints like velocity control, position control, effort control joints, but it can also be sensors like an IMU or a force torque sensor. So if we keep on moving to the left, then we can see that there's this column of a set of controllers. So controllers are elements that make use of these resources. And for example, we have the example of a mobile-based controller. We have an ARM controller. And then we can have, custom controllers. So further moving to the left, we can see that there's a third-party block where you can see higher level functionalities, like, for example, the ROS navigation stack or Move It. And then at the leftmost position, you have your actual application that brings it all together and actually makes sense of this whole set. So what does this mean for ROS Industrial and how both projects can benefit from each other? So if we go again and see the rightmost part of the image, when you leverage ROS control, what you actually have to code for yourself is the hardware backend for your robot. In this case, for ROS Industrial, you would use the ROS-I client for this, but you could leverage out of the box the gazebo bindings, which as far as I'm concerned, ROS Industrial right now doesn't have out of the box generic integration with gazebo. And this is, I think, very important, not only because of the physics, but because it also allows you to integrate perception in your simulation. Regarding controllers, ROS control already has a pretty decent set of controllers that are available out of the box for navigating mobile bases, but also for interpolating trajectories, and exposes the interfaces that Move It expects. So in this case, it's very likely that potential users will leverage some of the controllers that exist, and maybe if you do have to write a controller, it would be probably one controller or not much. Since we have controllers that expose standard ROS interfaces, it should be rather straightforward to integrate with things like navigation and Move It. In fact, we have already done this. And so the idea with all of this is that if we now take a look again at the leftmost corner, is that the time that you're not spending implementing low-level stuff is time that you can reinvest in your application. And actually the vision of ROS control is that it should allow you to maximize the resources that you spend on the actual client application, which is in the end your bottom line. I think that pretty much concludes what I want to say about ROS control and ROS Industrial.
Okay, thank you, Adolfo. As with the other lightning talk, we will collect the answers and do a question-answer session at the end of the lightning talk session. So I will change.
I'm going to
Oh, yeah, sorry.
a URL for project so that you can take a look at it because it was not present in the presentation. And
Okay.
Thank you. Thank you so much.
Okay, so the next talk will be given by my colleague Rames about the UROC project. Yeah, hello. So basically, the UROC project is one of the last projects funded under the Framework Program 7 of the European Commission. It's very similar to the DARPA Grand Challenge, only this time in Europe and with another set of tasks. So the idea here was basically that we want to, instead of having the usual project proposals, we would like to have an open call where basically there are 3 different scenarios. One is reconfigurable interactive manufacturing cell. The second is shop floor logistics and manipulation. The third is plant inspection and servicing. So those are the 3 different scenarios, and for each scenario there are 3 stages with increasing difficulty. And the idea is to get the best roboticists in Europe to work together with technology developers, system integrators, and work on real industrial use cases, so that at the end we can evaluate the approaches and provide a benchmark of which approach, which algorithm, which hardware component, which software component would be the best to solve those issues. So next I will be focusing a little bit on Challenge 1 because this is the one that IPA is hosting. Basically, the scenario, we will collect from end users a couple of basically use cases, and the idea is that challengers, if they actually advance to the second stage, they are able to choose one of those use cases to implement. Stage 1 is a simulation contest, basically with Gazebo and some simulation tasks that we as EUROC provide to them. Second stage is, as I said, realistic lab. Challenger teams can come into our lab. We will provide the hardware. We will provide also a little bit of support regarding software integration and so on. And they can implement a specific use case. And the third stage is at the end user side to implement a system which is running in the production system of the end users. So part of the prerequisites or requirements for Challenge 1 is basically we will provide the hardware, and this hardware will be connected through a ROS framework. So if the Challenger teams request from us support, they have to also implement their software components and algorithms in ROS. This is actually a nice thing because on the one hand we try to advance a little bit ROS Industrial in the community, also in the industrial community, and on the second hand we got a little bit of funding to implement some of the drivers where we see that there is a need, there is a demand behind them. So we agreed already on a UR5, UR10 driver, KUKA EVA, Shunk, lightweight ARM 4P, couple of grippers and a couple of sensors. Those are already on the roadmap to be implemented in EUROC, and we will collect from the Challenger teams additional hardware components which they want to use in their solution and which we will provide the ROS drivers for. Okay, that's it. Okay. So thank you, Rames. And again, if you have questions, just post them to the chat window, please. And I will take the opportunity to also give you a short overview of some updates we have in the Bright project. I gave already a presentation about the Bright toolchain, the last ROS Industrial Community Forum. But for all of you that didn't attend that, just a small overview. Bright is basically a Eclipse-based model-driven engineering toolchain for ROS developers. So you can basically create models in Eclipse of your components, and most of the code of these components, either in C++ or Python, will be generated automatically, and also most of the meta files we have in ROS, like launch files or package XML files and so on, will be created automatically. And the goal is basically that you enhance reuse inside ROS, because you describe the properties of a certain component more formal with the modeling toolchain. And as I said, I gave a presentation about the toolchain already last meeting, so please just look into the video of that if you are interested in more details. I just want to give you some updates of the project. So some new features which just came out. So we integrated now wizards for creating projects with a specific setup for ROS. So you basically can create a new project and everything will be set up for C++ indexing. You can just use the Eclipse build to actually utilize the catkin make, and that makes setting up Eclipse much easier. And also we have an import wizard now, where if you have already existing projects or catkin projects, you can just import them into your workspace, and also there you have all the C++ indexing and so on. And that's not only useful for Bright users, like native Bright users that use in model-driven parts, but also if you are just generally using Eclipse, you can use Bright and make use of these settings. Another couple of new features are on the template and model, the meta model itself. So we support now XML RPC values as parameters. That's something we didn't support before. So you can like use vectors and so on as parameters. Also, we can it used to be that topics are published and updated on every update in the main loop of the component. And you can now activate and deactivate topics if you don't want to publish on every update. And also in the current release, we have a lot of bug fixes and a lot of small workflow improvements, like for example that you when you create a new model, it also already a lot of things are auto-filled, like if you do a catkin create package where you basically the author, email, username and so on is already filled out. We have a similar behavior now also in Bright. And in the end, we also have some updates regarding the project itself. So we just triggered a release last week. It's a release 031. It's already in Shadowfix, so with the next sync in Hydro, you should also have it on the normal ROS package server. We have our two research projects where we have the capability of actively developing bricks with a bigger bandwidth now with Factory in Day, and also a German project that just started. It's called ReApp. And because the mailing list that we used was still on the Bricks server, and Bricks is over now already for some time, and so we created a new mailing list just to make sure that the mailing list stays online. So there's a new Google Groups mailing list now, which we can basically use for announcements and discussions. And because it's not only about Bright, or should not only be about Bright, but about model-driven engineering in general for ROS, we just named it ROS MDE. And in the end, I just want to say a lot of people already gave feedback on Bright, and most of the improvements we have in Bright are based on that feedback. So I want to thank all of you that gave feedback already, and please continue that because I think it's still a low release number, and there's still a lot of room for improvement. So please give feedback, use the GitHub issues or the mailing list, and tell what you like or what you don't like. So thanks, and that was this talk. And so now we have basically a couple of minutes for discussing the topics of the lightning talks. So the first question was actually on, there was a question on the first talk of the industrial calibration package, and Adolfo was asking why the camera is not on the end effector. Can the calibration procedure estimate the joints 0? So Chris, can you answer that question? It was a little bit up the chat.
Yes, I'm not sure I understand the question.
Kinematic calibration of the robot, right? Can your package be extended to calibrate the robot kinematic?
That was the idea behind the last question of a need, is that how do you calibrate how do you determine the Devenant-Hardenberg parameters of the robot is sort of an extension of how do you calculate the transform between the camera and the end effector when it's attached to the thing. So we don't do that at this point.
But we have plans.
We're considering it, but we don't do that.
Okay, so Florian is repasting the questions into the chat, so you can see it. So the next question was on, also on the calibration toolkit. So could you elaborate on why you opted for creating a new package instead of extending the existing camera calibration package?
Okay, so the existing camera calibration package uses OpenCV for its solving the bundle adjustment problem, and we wanted to use the SwRI optimization package for that. And in addition, it's not very, it's not easy to change how the reprojection models work. I mean, there were just a lot of failures in that package for collecting, like doing intrinsic calibration, for example. It basically just collects a whole bunch of images while the target is moving in front of the camera, and doesn't require you to have a stationary scene, which in our goals is to make it a highly accurate calibration, would require you to be able to trigger every single image that you capture. And so it was just a major change from the current mode of operation of that calibration package.
Okay, so thanks again for that interesting lightning talk. So now we come to the questions to the second lightning talk on ROS control. So Florian just pasted in the question, is there any option for LiDAR extrinsic calibration using that tool? Oh, sorry, it was still on I think it was still on the image, in the calibration toolbox, sorry.
Yeah, we currently do not support LiDAR. We would have to add basically all the different parts that would be necessary would be some sort of a target. What's the target definition? I'm not sure if there's a standard target that's being used for LiDAR calibration, and we would then have to have a reprojection model. So how do you determine the error between what you expect to see and what you actually observe from the thing? So you'd have to write another custom reprojection error model. And that's essentially why we moved to SwRI rather than OpenCV, is that it will support those kinds of things, but we currently don't support that.
Like a good Google Summer of Code project.
Okay, now thank you again for the interesting lightning talk. So now we come to the questions about ROS control. So the first question is from Florian, actually. So actually, Florian, you can answer a question. Okay, yeah. So can you deal with multiple hardware interfaces? In your drawing, you had only one hardware interface block. What about having like multiple bus systems or something like that?
Okay. it is possible to have multiple hardware interfaces in a single controller. In fact, we have an example that does it, which is a biped controller that uses joints for controlling. It reads the joint state, but it also commands the joints. But additionally, we read IMUs and force-torque sensors in the ankles in real time. So this would be an example. I do have to say that there's inside ROS control, there is currently a bias towards having controllers with a single interface. So I would expect that in the future, supporting multiple hardware interfaces should become more straightforward. But from a technical point of view, it's possible, and it has been done. There was also another question on ROS control, which was how is the real-time the real-time parts actually implemented? I would like to address that one as well. So actually, ROS control does not make any assumptions on whether there is a real-time operating system in place or not, and if there is one, which you are using. So in fact, that's actually up to you. If you want to use, I don't know, Xenomai or VxWorks or the RT preempt patch, it's up to you to set that up and then wrap the ROS control code inside a thread that has real-time privileges. But the thing is that when we say that it's real-time ready, what this means is that the implementation is such that it doesn't do things that will break your real-time constraints. And this is basically Linux system calls or system calls. So typical calls that you should not do in a hard real-time context are dynamic memory allocations, things like querying the system clock using like a Linux system call. Also, usually logging systems are non-real-time, and depending on the case, certain concurrency mechanisms like condition variables can also be non-real-time safe. So if you use ROS controller, one of its controllers, then you have the guarantee that if you run them in a real-time context, then you won't have real-time violations. So that's pretty much what we mean by real-time ready.
Okay, thank you. Okay, there's another.
I just thought that there's another another question. I might as well take the opportunity to address it. So the question reads, is it possible to develop custom controllers, for example, a cascade controller? It is perfectly possible to implement a custom controller. In fact, in the end, all of the controllers that are implemented already in ROS control are in a way or another a custom controller. So you could write a controller that might be, for example, robot specific, that you cannot generalize it across other robots because it depends on interfaces that no other robot but yours has. I don't know if maybe the question about cascade controllers means of concatenating, feeding the output of one controller as input to the other in a sort of like a computational graph layout. So this is not currently supported in ROS control. So things like perception or control pipelines, this has been discussed quite a lot in the mailing list, but the current interfaces do not allow you to do that. If you wanted to do it, you would actually have to bundle all of that code inside one controller plugin. That would be it.
Okay, thank you, Adolfo. So I think that these were all questions about the lightning talks. We still if you have questions in general regarding ROS Industrial, you're also free to ask them. And maybe we can discuss them, but of course, discussing them on the mailing list or something is probably better because everyone can speak then. Okay. So if there are no further questions or proposals for discussion, I wonder in the end now also present some upcoming events of the ROS Industrial community. So actually on Wednesday already there will be a road mapping web workshop on discussing about the ROS Industrial Consortium roadmap. Okay. Yeah, okay, I will answer that question in the end. Then there is a training class in San Antonio from in May actually, 19th to 20th of May. And then in Europe there's a big industrial fair in Munich called Automatica. And on that industrial fair there will also be a ROS Industrial booth. So if you are on Automatica or around this region, just come to the fair and visit the Fraunhofer IPA booth, and on that you will find the ROS Industrial booth, and you can talk to any of us. Actually, I think the Automatica is from June 3rd to June 6th. Sorry for that. So it's a one-day shift. Then on June 26th, there will be an open ROS Industrial workshop. So it's an open workshop, everyone can join, and we have a couple of speakers. You can find that on the ROS Industrial Europe page. We have a couple of speakers, and then there's also a lot of room for discussion about roadmaps and so on. And the next day after the June 27th, there will be the first consortium meeting. We will start the ROS Industrial Europe consortium on that day with the European partners, and we will also take the chance there to speak a lot about the first projects, the first roadmaps, and so on we will implement. And then on July 15th, the date is just a one-day workshop, but the conference is from July 15th till 19th, and it's not fixed yet on what day the actual workshop will be. But on this on the conference in Padua, there will be a workshop on ROS Industrial in European research projects, because there are already a lot of European research projects that are somehow connected to ROS Industrial, and we will discuss that on that workshop. And then the question was if there will be also a training in Europe for ROS Industrial, and yes, actually there are regular trainings at Fraunhofer IPA, and the next there was one in March, and the next one will be in October. So we have the date. Okay, yeah, we will post the date later on the chat or in the minutes. Okay. So, but it will be in October. Okay, so if there are no further questions, then I want to thank everyone for joining that community meeting. Also, thanks for SwRI again for the any meeting setup. It will probably not be the last community forum, so there will probably be more. And thanks again. We had over 40 participants this time, thank you, and give us feedback what you think about the community forum or ROS Industrial in general, and I hope to see you soon on some of the occasions we have in the next month. So thank you and goodbye from IPA.